And yeah, as you can see here, all of the traces have different MD5 checksums, so they are different actually. But we will now try to extract a signature from these. Okay, I'll now start the Nebula daemon. The Nebula daemon is the signature generation engine. You can provide it with a secret so that you can, submit inputs to it in a secure way. How do I open the second tab here? Okay, and the Nebula package, which is open source, you can download it and play with it yourself, also comes with a command line client to submit files to it. Okay, I just did that. I submitted the 20 files. I guess I missed a parameter here. Yeah, I have to tell it that it should start generating signatures as soon as it has at least 20 traces from one particular attack. And I'll do so now. I'll do it again. Yeah, and as you can see here, a little bit, it's not so easy because the line sizes. Yeah, okay. Yeah, it basically generated this NOT signature, which identified as invariant parts the GET request, the start of the GET request, user agent string. I don't know what that is, probably some, yeah, to have the right offset or stuff. And here's the binary data, which is a GET-PC sequence. As you might know, in a shellcode, you need to, in most cases, you need to determine where the program counter points to. And this is a typical sequence. I guess we will have that in your part as well, in more detail. This is a GET-PC sequence starting with a jump, another jump in the core, and this is static over all traces. The short content parts here are probably crap, like noise, and if you would provide more than 20 traces, like 100 or 200 traces, they would probably get eliminated. And the authorization basic part is constant over all traces, so it's completely copied into the signature. And you can now use this signature within Snort to detect exploitation attempts of that kind. Yeah, we don't have more time to talk about signature generation here in more detail. I'll now hand over to Markus, who will give you an introduction to automatic shellcode analysis.
Hello, I'm Markus, and I'll try to explain the basics of detecting and profiling shellcodes from network streams. So taking the technology Till just presented, we can gather a lot of data, and we need a way to automatically look for shellcode within this data. And there are several different approaches to detect shellcode. But the most known approach is manual analysis. Manual analysis is pretty time consuming and it requires Windows. And as Till already mentioned, we were looking for something to make Linux exploitable to Windows exploits. How to detect shellcodes? There were static approaches, detection of NOPE slides. It's pretty historic, nobody does it anymore. There are too many possibilities to create valid NOPE slides. Detection using pattern matching for the decrypting part of a shellcode works, but the more patterns you have, the slower it gets. And it's pretty easy to create new decoders which do not match any signatures. And there were some dynamic approaches, and these are titles of publications. It's about detecting shellcodes, self-decrypting shellcodes, using a technique which is called GET-PC. Self-decrypting shellcode got a stub in front of the actual payload, and this stub is meant to decrypt the shellcode. You have to encrypt shellcode if you want to avoid certain patterns, for example, a string terminating 0 or something else. And you put a stub in front of the shellcode, which decodes the shellcode before you have encoded it with a XOR pattern or something like that. To be able to decode the shellcode within memory, you have to know where the shellcode actually is. And as you can't access the program counter or EIP register directly, you have to retrieve this, the address. And there are two possibilities to retrieve EIP. One is call. EIP gets pushed on the stack, and you can pop it, or using FPU commands. Looking for these instructions is pretty cheap. There are just 1 or 2 bytes you have to check, and can be done in real time, more or less. The problem about this was all just paperwork. They just said it works, and we did some research on it, but nobody published code. So we had to do our own. We started a project called libemu. We took the knowledge gathered from the papers to implement a small x86 CPU to detect shellcode in network streams. We wanted to use the getPC heuristics just mentioned, binary backwards traversal, I'll explain it later, and instruction dependency tracking to detect shellcode. Furthermore, we wanted to allow shellcode emulation. Once we detect it, we might want to execute it and publish the code before publishing anything else. So, as mentioned previously, how to detect the start of a shellcode. We are looking for getPC sequences. And once we found a getPC sequence, we can't be sure it's actually shellcode. It can be anything. So there has to be a way to check if it's really shellcode. Others have proven that the occurrence of a loop after a getPC sequence is a reliable indicator for shellcode, or 7 payload reads, or 32 steps after the getPC sequence. Going further, we said if you got an AP call within a network stream, it's shellcode too. What now? We need to be able to execute the shellcode within an emulated environment. This emulated environment is a process environment of Windows. And we have to be able to hook AP calls. So we see which AP is meant to call. For example, if the shellcode wants to download something, we want to know where it wants to download from. If the shellcode wants to connect to somebody, we want to know where it wants to connect to. And we've had a lot of problems. One problem was Windows. And the Windows problems were about the process environment block, the DLL loading. A shellcode has to resolve addresses from functions, and it takes a real procedure to get the address of a process function in Windows. On Linux, it's just calling an interrupt. So we have to map the process environment block of a real Windows process to our process environment within our emulation, and the exports of a DLL, of several DLLs as well. For example, we have to provide the exports of kernel 32 DLL and W232 DLL and some others. And another problem is shellcode can have initializing seeding functions before getPC. So we found getPC, and we start executing the shell. You're starting to sleep. There is a chair free in the front. I'll show it in a picture. this is the getPC sequence. You can't see the call, but it's the box above the arrow which is green. I didn't expect it being... So, the problem is we start executing the shellcode in the middle, and there are instructions in front of the shellcode, in front of the getPC sequence, which are required to make the shellcode work. For example, here is a loop as an instruction, and what? And loop requires the ECX register to be initialized, but it was not initialized before. To be able to execute the shellcode properly, we have to look for the instruction which initializes ECX properly. Can you see the red one now? The red path is the one which initializes ECX. And once we start execution on the proper beginning, we can access the encrypted shellcode. Now I'll try to give a short, brief demo of how to use it. We got a small command line interface to the library, which allows executing Windows shellcode on a Linux system, and you can create graphs of it. The command line utility is called sctest, and we will run several different things. The second one means interactive. Interactive allows proxying operating system calls to the host operating system. So if the shellcode wants to download something, it downloads something. This allows tracking shellcodes which consist of multiple stages. The first stage just exploits and opens a port or something like that, and then accepts a connection and executes the data which comes from the accepted connection. To be able to profile such shellcodes, we have to be able to run them interactive. And the other thing is you can create graphs of the shellcode. How does it work? So you can see which AP calls are met and which loops are in there.
Yeah, I assume that there are no open questions to that part, so we can safely skip the demo. No, okay.
Du kannst auch was zu sagen.
Yeah, the thing is that it's actually a nice tool and it's great. Yeah. But it's not so easy to talk about. Okay, Marcus is now running sctest, which tests the file piped into it and checks it for shellcodes. Minus G means getPC. Yeah.
Minus G means detect the start of the shellcode using the getPC thing I tried to explain. Minus S means run about 10,000 steps, so it doesn't run forever. It stops after 10,000 steps. Won't be enough. It's Windows shellcode. And the large S means read the data from std_in. So after 177,000 steps, we can see what the shellcode did. It loaded the library, the WS232 library, which is required to do network communications on Windows, WS Startup, WSA Socket, bind, listen,